All right, good morning. We are going to be focusing on in this next objective, talking about something called isotopes and how to calculate the atomic mass, which is a weighted average. So before this point, we've already talked about protons, neutrons, electrons, how to determine them. We've also already talked about atomic number and mass number. So let's first just get into defining isotopes. So oxygen has three known stable isotopes. So oxygen 16, oxygen 17, and oxygen 18. And these are isotopes of each other. All right, well, what's the same between them, or what's their similarity? We can see that they're all oxygen, so they're all the same element. Okay, but there's obviously this difference between them. And if you remember, the 16, 17, 18 are all mass numbers, which means they have different mass numbers. Okay, so that's one initial definition of an isotope. They're the same element, but they have different mass numbers. A lot of the time, though, we're looking for, well, what's their difference in terms of those subatomic particles? What's the same in terms of protons, neutrons, and electrons? Or what's different between your protons, neutrons, and electrons? So that's where we're going to define that part down here. So in terms of our subatomic particles, so the particles within an atom, isotopes, if they're the same element, and think about atomic number, if they're the same element with the same atomic number, they have to have the same number of protons, because we know that all oxygen atoms have to have 8 protons. So what then is making them different in terms of their particles within the atom? Well, we know they have different mass numbers, and we know that mass numbers are your protons plus your neutrons. So if your protons are staying the same, it must be that isotopes have a different number of neutrons. Okay, so those gives you two ways to define an isotope. And then we're going to start to work our way through a couple of practice questions of what you might see in terms of a Regents question. So going down to these questions down here, which two notations represent different isotopes of the same element? So the first thing I'm going to look for is just getting rid of anything that's not the same element. So these two are not the same element, and these two are not the same element. So then I'm looking at these guys. Well, remember, they are going to be the same element, but they have to have different mass numbers. So in this first one, they both have a mass of 7, so they can't be different isotopes of each other. These are the same isotopes as each other. If I look at number 4, though, they're the same element, but they have different mass numbers. So this would be a pair of isotopes based on their notation. Okay. All right, number 2, if two atoms are isotopes of the same element, the atoms must have. So the first part of this statement, okay, is dealing with protons. So we know that isotopes, okay, have to have the same number of protons. So I can get rid of number 1 and number 4 because they have to have the same number of protons. Okay, and based on what we just talked about in terms of our definition, do they have the same or different number of protons? Well, they have to have a different number of neutrons, sorry. Okay, so our only choice here would be choice 3. They have the same number of protons and a different number of neutrons. That just defines an isotope. Number 3, isotopes of an element must have different, okay, well, they have to have the same protons. Okay, electrons we haven't talked about, and we'll be dealing with that in a later unit. So if we're looking at mass numbers and atomic number, well, atomic number are your protons. Okay, so it can't be 4. So our best answer here is that isotopes of an element must have different mass numbers, which just goes up to the example of that we use with our oxygens. And then our last practice questions, we have these 3 nuclides of uranium, 233, 235, 238. Okay, they have the same number of protons per atom, and this last part is defining an isotope, number 3, a different number of neutrons per atom, okay, which is giving them those different mass numbers. Okay, so just making sure and checking in that you understand that definition that we just talked about. The other big part of isotopes is dealing with atomic masses. So on our periodic table, this atomic mass up here, you'll see is not a whole number. Okay, mass numbers are always a whole number. Okay, mass number, whole number. Okay, it's equal to the protons plus the neutrons. Okay, so it has to be a whole number. Our atomic mass, which you'll see in the periodic table, is not a whole number. And that's because we're taking a weighted average, kind of like when you have a weighted quarter grade based on different categories of assignments. And this is going to be a weighted average of all the naturally occurring isotopes. So they don't take into account any artificially occurring ones. Okay, and it's always going to end up being a decimal because of this weighted average. So this first practice question is just checking in with the definition. This is similar to like one you might see in a Regents question. So it gives us the atomic mass of titanium. It says that atomic mass represents what? So if you look through those options, the best option is that it has a weighted average, and it's going to be of all the naturally occurring isotopes. So choice 2. Well, how do we actually calculate this? And this is one of those skills that you're going to need to be able to do when we get to a quiz or a test or a practice. So chlorine has 2 naturally occurring isotopes, chlorine 35, and it gives you this more precise mass. So we're going to be using that. So this is my mass for chlorine 35, and then chlorine 37, which gives me this mass. The mass number and then this more precise mass, we're always going to use the more precise mass. So this is for chlorine 37. Okay, and it gives you their percent abundance. So this is basically how much of those naturally occurring isotopes can be contributed to chlorine 37 and chlorine 35. So 32.51 is chlorine 37, and then 67.49 is chlorine 35. So how do we actually calculate this? I'm going to show you 2 different setups that you could see in a multiple choice question, but that you can also use when you go to answer a short response question. So with this first part, I'm going to start with my 2 masses. So what I'm going to be doing, I'll kind of put this up here, is I'm going to take the mass of the isotope times the percent abundance plus the mass of the other isotope times its percent abundance, and then I'm going to divide it all by 100. So that's going to be my first setup that I'll show you. So with this part here, I have my 34.9689. Okay, that's my mass. I'm going to leave a spot for my percent abundance. I'm going to write the mass of the chlorine 37, which is 36.9659. Leave its percentage, and then I'm going to put it all over 100. Okay, so then I'm going to fill in the percentages, and I just did this separately because of how they're mixed over here. So this was my chlorine 35. Its percentage is 32.51, and then the percentage of the chlorine 35 is 67.49. Okay, when you plug that all into your calculator and then making sure you divide by 100 at the end, you should get here 35.62, and that would be in atomic mass units. Okay, one little way to check that is to make sure that it's between the 2 masses that were given to you of those 2 isotopes, which it is. Okay, you can also see that based on the percentage, there was a higher percentage of 35, so I would expect it to be a little bit closer to the one with the higher percentage. Okay, another way that you can set this up is you can take your percentages and divide them by 100 ahead of time. So one big thing is make sure you leave your masses alone. So these would be my masses. Okay, I'm still adding them together. So this is 36.9659. Okay, and then I'm going to divide their percentages by 100 ahead of time. So this would be 0.6749. Okay, I'm going to take this percentage, divide it by 100. So 0.3251, and that could be my setup instead. You just have to be really careful with your decimal places, and that will give me my same answer, 35.62 AMU. Okay, so what I would suggest is you pause the video, okay, and try out this second practice question and then compare it to mine. All right, so for this example, we're going to use the same initial setup, doing it over 100, but you could have done it with decimal form as well. Just keep in mind these are your percent abundances. So if you do divide by 100 in your setup, make sure you're dividing these and not your atomic masses. So I'm going to fill in my atomic mass for copper 63, so 62.930. I'm going to fill in its percent abundance, which is right next to it, so 69.17. I'm going to fill in the mass of my other one times its percent, and then I'm going to make sure I divide that and show that it's divided by 100. Okay, when you go ahead, and again, I should expect an answer between these 2 masses, and you plug that in, you should get 63.55 AMU, atomic mass units. Okay, again, if you did do the other setup, just to make sure you're doing it right, you should have written down 62.930, and then your percentage should have been the 0.6917 plus the other mass, and then that would have been divided in your setup by 100 ahead of time, and then you would have gotten the same thing. Okay, again, either one is acceptable. You'll see both options on like multiple choice types of questions, so you got to still be aware of both. And really, this one, you just got to be careful with your decimal point. Okay, so that covers everything. We went over isotopes and we went over atomic mass, so you should be able to do some practice questions moving forward.